Hi, I'm Sean with LNC Math, and today we're going to be talking about radicals. The first thing you need to understand before you do anything else with radicals is how to simplify radicals. Many radicals are easy to simplify if they're a perfect square. For example, 4 is a perfect square, so the square root of 4 would be very, very easy to compute because we know that 2 times itself equals 4. So the square root of 4 would be equal to 2. However, some other numbers are not as easy to compute the square root of. For example, let's take 50. 50 we know is not a perfect square, but it could be further simplified. When trying to compute the square root of a non-perfect square, we must think to ourselves, what perfect squares are a factor of this number? So it would help to know your perfect squares. Looking at this, I know a perfect square that is a factor of 50 is 25. So this can be rewritten as the square root of 25 times the square root of 2. Now that we've rewritten it like this, we can simplify the square root of 25 into a positive 5 because square root of 25 is 5. However, we cannot simplify square root of 2 because 2 is not a perfect square. So our answer remains 5 root 2. Now, sometimes you might find a variable inside the square root. When this happens, you would do something similar, except you'd have to use a variable. We have to ask ourselves, what perfect square is x to the 5th divisible by? A perfect square is a number that has a exponent of an even number. So, if we look at this, we know that x to the 4th times x is the same thing as x to the 5th. However, we can simplify the square root of x to the 4th because x to the 4th is going to be equal to, the square root of x to the 4th is going to be equal to x squared. Since x cannot be simplified further because it does not have an even power, we will have to leave it as square root of x. And since we had an 8 in the beginning of the equation, we have to multiply all of this by 8. Now, let's take an example where this is all combined. We have an integer and we have a variable inside the square root. So what I like to do is I like to work with the integer first. 243. Now that may seem like a big number, but let's see if we can simplify it even further. So 243, we can see that if you add the digits up, it's divisible by 3, because 2 plus 4 is 6 and 6 plus 3 is 9. So that 9 is divisible by 3. So 243 is divisible by 3. So let's try to simplify it and see if it'll get us anywhere. So let's take a 3, and if we divide that, divided by 2, this would be 881. Oh, look at that. We have an 81, which we know is a perfect square, because 81 is equal to 9 squared. Square root of 3 we can't simplify, so we have to leave it as that, but 81 would be equal to, square root of 81 would be equal to 9. Since we have the 9 here, and it doesn't have a square root, we can combine it with the 2 on the outside. So 9 times 2 would be 18. However, we still have this along with the x to the 7th. So we have times the square root of 3 times the square root of x to the 7th. We know the square root of 3 can't be simplified, but the square root of x to the 7th could be simplified. So what variable to an even power is divisible by x to the 7th? Is a factor of x to the 7th. The highest even number that could go into there would be x to the 6th times x. So we're left with the square root of x cannot be simplified further, but the square root of x to the 6th would be simplified to x cubed. And then we have our square root of x on the outside. So since this is part of the outside, we can combine it with the like term with the 18 times x cubed, and whatever is left on the inside, since they're both square rooted, we can multiply the insides and put a square root all over everything. 3x. And that's your answer. Let's move on to addition and subtraction with radicals. So, when we have two radicals, but they don't have the same number inside, we can't add them together. However, we must simplify them and see if we can add the like terms. So, since we know 75 and 27 are both not in simplest radical form, let's simplify them first. Looking at 75, what square number is a factor of 75? If we think about it, we know that 75 is equal to 25 times 3. Square root of 25 is equal to 5, and we know that square root of 75 is 5 root 3. Let's look at 27 now. Looking at 27, we know that 9, which is a perfect square, is a factor of 27. So, it is equal to square root of 9 times square root of 3. Square root of 9 simplifies to 3, and the square root of 27 simplifies to 3 root 3. So now we have the same number that's inside the radicals, which means they are a like term. That means we can add them, add the outsides, so that you have 5 square root of 3's over here, 3 square root of 3's over here, and if you add them together, you get 8 total square root of 3's, which is 8 root 3. Subtraction is just the same thing. You want to simplify your radicals first, and then you have to subtract the like terms. Here, we already see that 6 times the square root of 2 is already in simplest form because the square root of 2 can't be simplified further. However, square root of 32 can be simplified more. Looking at 32, we can see that 16 is a factor of 32. So, let's rewrite it as square root of 16 times the square root of 2. We know the square root of 16 is equal to 4 times the square root of 2 over here. So if we bring it all down, we can rewrite it as 6 root 2 minus 4 root 2. Since they both have the same number inside the radical, they can be subtracted. 6 root 2's minus 4 root 2's, and you're left with 2 root 2. Multiplying radicals is much easier. There are two ways you can multiply radicals. You can first multiply the numbers inside the radicals, or you can simplify and then multiply. For me, I think it's easier to multiply first and then see what it simplifies to. So, if you have 2 square roots and you multiply them, all you have to do is multiply the numbers that are inside. Square root of 2 times square root of 8 is the same thing as 2 times 8, which is 16, so square root of 16. Looking at 16, we already know that the square root of 16 is equal to 4, because 4 times 4 is 16. It's that simple. You could also simplify square root of 8 first and then multiply. So square root of 2 times square root of 8. Square root of 8 is equal to square root of 4 times square root of 2, and square root of 4 is equal to 2. So square root of 8 is 2 root 2. Square root of 2 times 2 root 2, and then if you multiply the square root of 2 by the square root of 2, you get 2, and 2 times 2 is equal to 4. For me, this is much easier, but it's really up to you. If you have variables, it's just the same thing. Since we have the 2 square roots right here, we can ignore the 2 for now. Multiplying the square roots, we get x times x cubed is x to the 4th. So if we simplify this, that'll be equal to x squared. If you're struggling to understand the power concept, just think of the square root as being to the power of 1/2. So if you multiply right here, you have the square root of x to the 4th, and the rule of exponents is if you're raising to another power, you multiply. So if it's x to the 4th to the power of 1/2, 4 times 1/2 equals 2. So that's how you would solve that. So we have the x squared, and we can bring back the 2, and the answer would simply be 2x squared. If you want to use cube roots, or even fourth roots, fifth roots, and so on, the methods are very, very similar. The cube root of 54, we'd still find factors of 54 that are cube roots, except this time we're not using perfect squares, we're using perfect cubes. Perfect cubes are harder to find because not many people memorize them. But once you have them memorized, it'll be really, really easy and you'll get them in no time. So for me, if I look at this, I see that 27 is a factor of 54. Now, you may not have seen that at first, but if you can prime factorize or even guess and check, you could probably find that 27 is a perfect cube. 3 times 3 times 3 is equal to 27, so the cube root of 27 would be equal to 3. Since there is no perfect cube root of 2, we would just leave it at cube root of 2. The answer for this would be equal to 3 times the cube root of 2. For variables, it's just like if you used perfect squares. Instead, this time we're looking for perfect cubes. Now this may look somewhat confusing, but if we use the trick I showed you a little earlier, this would be equal to, instead of 1/2 to the power of 1/2, it would be used as to the power of 1/3. So we can rewrite this as x to the 7 to the power of 1/3. Since they have exponents, we can multiply them. X to the power of 7/3. 7/3 can be simplified to and rewritten as x to the 2 1/3. So we can have x to the 2, x to the second, and then x times x to the 1/3. So x squared times x to the 1/3. And working backwards using this, we can know that x to the 1/3 would be equal to the cube root of x. So x squared times cube root of x would be your answer. And if you wanted to do this a little faster, you just look at the number on the outside and the number on the inside. However many times the number goes on the outside goes into the inside. So 2 times 3 means it would go in 2 times and there'd be 6. There's one remainder, so there's 2 on the outside and 1 on the inside. Now, combining both those, what we just learned, let's try it with a 5th root. Now, I'm pretty sure that none of you have memorized your 5th roots, and I haven't either, which is perfectly fine. So if we look at 32, let's just see what numbers go into it. It'll also be a lot easier to prime factorize as well. So 32 is 2 times 16, which is equal, 16 is 2 times 8, which is 2 times 4, which is 2 times 2. Would you look at that? There are 5 2's, which means that 32 is equal to 2 to the 5th. So the 5th root of 32 would be equal to 2. Now let's move on to the variable. Using what we learned over here, we would look at 12 and see that 5 would go twice into 12 with 2 as a remainder. So that means there would be x squared on the outside, and there's an x squared on the inside, times 5th root of x squared. There you have it. That was our first part of radicals. Next video, we're going to be working on dividing and conjugates, which is kind of annoying, but see you till then.